All right, so questions, comments?
I didn't see an ODP for today.
There's no ODP for today. You got the day off. So I'll post an ODP Tuesday morning. That'll be due Wednesday, but none today. All right, well, I'd like to quickly talk about the ODP that you finished today and make sure people are good with that. Make a few comments on PA1, but mostly I want to talk about PA2. And then we'll talk about some memory issues, and then we'll start writing some code to manipulate linked lists in the style that we're going to build them in PA2. So let me just start with ODP 207. So this was your link function that takes two nodes and links one to the second, and it really is one line of code. So you take a node n1 and n2 and you say n1 arrow next equals n2, and that's really all you got to do. The trick is there's so many different one lines of code that we could try, and figuring out that this is the right way to do it is something that takes practice and will make perfect sense at some point, if not already. So what does this mean? Struct Node. So n1 arrow next equals n2. So here's a struct node. Here's another struct node. I'm calling this n1 and n2, but remember, n1 is just a number. It's not actually a structure, it's a number. That number is a location in memory, and if we go to that location in memory, we will find a block of data that stores a number, and we'll find following that a block of data that stores another address. So the data field in the next field. And so n1 arrow next, that says go to the memory to which n1 points. That's this block. Pick out the next field. That's right here. And set that equal to n2. What we're putting in here is basically the address of n2. But whenever we use this address to find a field in n2, we're going to say whatever that variable is, arrow next, or arrow data. So if we say struct node temp equals n2 arrow next, then temp becomes the value of this field, which is the address of n2. So now temp is actually pointing to n2 also. And if we said something like temp arrow data equals 15, that's going to put a 15 right here. But since temp is just n2 arrow next, we could also have said n2 arrow next arrow data equals, and we could set that to 100. That's going to put 100 right here. And the way we read this is n2's next field is a node. Take the data field of that, set it equal to 100. Yeah. This is all n1. Thank you. And if this next field is pointing to some other node, we could say the following: n1 arrow next. That's this node n2 arrow next. That's the next field, which is this node arrow data equals minus 17. That's going to put a minus 17 right here. And the way we read this is n1 next, that's this, next, that's this, data, that's that field right there. Now we don't have to be able to write things like this. We can use temporary variables. We could say n2 equals n1 arrow next. We could say n3 equals n2 arrow next. And think of this as n3, and then we could say n3 arrow data equals negative 17. And it'll do the same thing as this. But at some point, this will start to be how we sort of picture these things in our heads. And sometimes it's easier not to have temporary variables like this, but you can always put in temporaries. So one line for the link function, but it's got to be the right line. And there's lots of versions that aren't quite right. I posted an announcement also. Be careful what you name your programs when you're assessing them. If you name it test or link or GCC or something that's already a built-in command, assess may run that command instead of yours when trying to assess. I think you could say assess./link and it would work, but if you just stick to calling them main 205, main 206, there's no danger of confusion there. So let's talk about PA2. So the description is almost exactly the same as PA1, and the execution of the program is indistinguishable from PA1. Insert 5, insert 2, print. Delete 4, delete 5, print. Search for 2, search for 5. Unknown, exit. So it's gonna, when you run PA2, it's gonna look just like when you're running PA1. So your linked list is constructed of these modified nodes. So 2 pieces, a data and a next, no valid flag anywhere in here, no arrays anywhere in here. Okay, so your struct node looks like this, where the next field is the memory location of the next element, or for the end of the list, we're going to use null, uppercase, instead of my null. So no my nulls anywhere. Okay, in your main program, your list is going to be a struct node star, just like it was in PA1. You can call it list, LL, whatever you like. But in this case, it's going to actually point to the sentinel node, which it kind of did in the array case also, but it's just the address of the sentinel. All right, and you're going to write 5 functions that main is going to use. Init is the one function that has a different prototype from PA1. PA1 we called init and we passed it the array. In here, we don't pass any argument to init, and it returns a struct node star. And what init's going to return is the address of the sentinel. So in our main program, we're going to say something like this. So you have your struct node list, that's your sentinel. And we're just going to say list equals init. Instead of init parentheses list. Sorry? That one? So just list equals init. So PA1 we said init and we passed the array. Here we're getting the address of the sentinel node, storing it in list. all the other functions exactly the same prototype as PA1. So your add function takes a struct node star and it takes an integer and it adds that to the list in the right place, smallest to largest, returns 1 if successful, 0 if not, because there's no memory left. And then print, delete, search, exactly the same as before. So the implementation will be different, but to your main program, other than the init function, all of these have exactly the same structure. So your main program is barely going to change. Your one line where you call the initialize function will change, and there'll be one extra thing we have to do at the end, and I'll tell you what that is in a moment. But other than that, your main program should be exactly the same as PA1. Except your comments will say PA2, etc. All right, and again, this is the view as an abstract data type of how we interact with a linked list. So the main program never calls malloc, it never calls free, right? It only interacts by using these 5 functions. And that's an extension of what we did in PA1. Let me make a comment up front. In PA1, I tried to give you some direction in terms of making sure main only interacts with the linked list through these functions, making sure your valid flag is only dealt with in 2 functions, get node and release node, and making sure that when you process your list, you're starting with a sentinel and following the links from one node to the next. Okay? If you have done that, then not only do you get full credit for that part of the grading, but PA2 will, everything I'm saying about PA2 applies, right? Same main program, minimal changes. In some cases that I've seen so far, people were not necessarily following that path on PA1. For example, in their search function, they say for I equals 1 to 100, if the data is equal to my number and valid is equal to 1, then return true. And that works. It tells you if the thing's in your list, but you're not treating it as a linked list. And you can't do that same algorithm in PA2 because we can't go through all of memory and search for your number. We don't have a nice array with everything all together. Same thing with print. We can't just march through, right? So if you didn't follow that path very closely in PA1, you're going to have extra work to do in PA2. But at the end of that work, you'll be back on that path of working with a list as an abstract data type and accessing your structure by starting with a sentinel, following the links from node to node. Okay, but if you did it PA1 the way that I said to do it, right, then everything I'm saying here is true. Main program is going to have 2 very minor changes. The way you use all these functions will be the same, and we'll actually look at how the code changes from PA1 to PA2, and you'll see it's very minor. Okay, not a lot else to say about PA2. The main program is the same, the requirements are the same, the error handling is the same, the deliverables are the same. Okay, so all your source code, a make file, lots of comments, comment block, put everything into a tar file, upload it to Canvas. So the only thing that changes is the implementation of these 5 functions. So any questions on that from a high level?
Version of the PA1?
Sorry?
Is it version of PA1?
I'll show it to you next week. My version? Yeah, I'm going to show that next week because there's a few people who haven't turned it in yet. But I got 61 submissions out of 65 turned in on time, which has never happened before. That's like a world record. And 2 of the missing 4 talked to me right after and told me what was going on. And I think there's 2 people who were enrolled in the course but not actually participating because they haven't done any ODPs. So this was really good. All right, so thank you for
There's some parts of it I'm not entirely sure exactly
There's
what
what?
you're supposed to do.
which one?
I don't remember what the top stuff.
Okay. All right, so there's no get node function that you have to write here. Okay, why is there no get node that you have to write?
Because you're allocating and freeing memory.
Because you're allocating and freeing memory using malloc and free. So when you want to allocate, when you want to get a node, you're going to call malloc. When you want to release memory, you're going to say free. And if you want to keep your get node and release node functions, right, you can keep those, and inside there, instead of searching your array, just call malloc. And in release, instead of setting the valid flag to 0, just call free. So those parts of these functions don't necessarily need to change either. In your add code, when you say get node, you can still call get node, but get node will just do a malloc. Okay, there's one other change though to this program versus PA1, and this is really important. The X command, after you're done with the program, you want to free all of the memory that you allocated. And we didn't have to do this in PA1 because we just had an array, and we don't free arrays when we're done. We just exit. And that's okay, because an array, in our case, it was only 100 struct nodes. But this linked list, right, we could be building a list with 1,000,000 nodes in it. And so that's 1,000,000 times the size of a node, blocks of memory. So the X command, before it exits, should actually free all of the allocated memory. And let's look at how to do that. So let's do a release all memory. And we'll pass it a pointer to the sentinel node, okay, our struct node star, which I sometimes call a header, but it's the thing that points to the list. So how do we release all the memory? And let's draw a picture. And here's list, it's the sentinel. Well, pseudocode wise, it's pretty straightforward. So here's some pseudocode. So free the node that you're pointing to right now. Point to the next node and go back up and just loop until list is null. Pseudocode. Alright, so free the node, move to the next node, free that, move to the next node, free that. Keep going until you move to the next node and you find that you're pointing at null, and then you're done. You freed all the nodes. There's one subtlety in here, which is that once you free a node, you're not allowed to use that node again. You're not allowed to touch any of its fields. So once I free list, technically I cannot say list arrow next. So here's how we could do this. Just use a temporary variable. So save equals list arrow next. Free list. List equals save. And just do all this until list is null. So as long as list is not null, save the node that it's pointing to. Okay, I'm putting that in a variable called save. Free the node that list points to, and then set list to point to the next node. Go back up to the top of the loop. As long as that's not null, save the thing it points to, free the node list, move to the next node. So it's not a lot of code, but you got to get it just right. And then the idea is in your main program, after the person says X, instead of just saying return, call your function release all memory or whatever you want to call it. and then return. So there's a program called valgrind that'll help you know if you released all of your memory. So let's take a look at that. So if you want to use malloc and free, you got to include standard lib.h. I'll go ahead and make this official. Alright, so there's a struct node, so I got 3 pointers to struct nodes. And I'll free all of my memory at the end of my program after I've allocated it. So this program doesn't do much, but it does some allocates.
So I'm going free.
Thank you. Thanks. All right, so 3 mallocs, 3 frees, and the order doesn't really matter. So let's run this. Doesn't do anything, right? But it did some stuff. Okay, so if you want to know, do I have memory leaks? Valgrind is the name of the program. Say valgrind space, and then whatever you would normally type to run your program. So for me, it's just haha. And it runs your program, and when it's done, it gives you this little report. So heap summary in use at exit 0 bytes and 0 blocks. Tells me I did 3 allocates and 3 frees, and I allocated a total of 48 bytes. So presumably my size of struct is 16. And since I allocated 3 of those, I got my 48. Here's what you're looking for. This message right here. All heap blocks were freed, no leaks are possible. You get your 5 or 10 points. It's usually 5 points for a memory leak. Alright, suppose you don't free all of your memory. Suppose I forget to free A. Question, yeah?
Oh no, it's just stretch.
Oh, okay. Suppose I forget to free A. So I run my program through valgrind, I get a different message here. It says, in use at exit 16 bytes in 1 block. Leak summary directly lost 16 bytes in 1 block. Okay, that's a memory leak. And it's leaking because I allocated something and I didn't free it. And if I'm super duper lazy and I just never bother to call free, my code will still work fine, but I'll get a bigger leak, right? So I had 3 blocks of memory that were in use when I exited, so I lost 48 bytes. And again, most operating systems, once your program exits, that memory is reclaimed. But some older systems, maybe not. Or small embedded systems, maybe not. So you write your code and you try to free all the memory you allocate, and then you run valgrind and it'll confirm whether that's happening or not. So PA2, when I test your code, I'll do one series of tests with valgrind. So when do you want to free your memory?
Or whenever you allocate it.
Whenever you're allocated and you're done with it, right? So when you delete a node, right? When you add something to the list, you allocate it, you're going to have to free that eventually. So if you say delete, you change the links, but you also want to call free on that node. so that releases it. And when you exit, you might still have stuff in your list, so now you do your release all memory function to traverse the list and release things in your wake. And if I try to free a block that I've already freed, I'll get some extra wordage here. Invalid free or delete or realloc at this location by main. This thing is 0 bytes inside a block of size 16 that was freed. So it's complaining to me. And what it's saying is I'm trying to free something that either was already freed or wasn't allocated in the first place. And they're warnings. You definitely want to pay attention to them. If you get messages like this, you're doing something wrong in your code. And sooner or later, it'll blow up.
So it's important that we allocate all free memory, but we don't
Don't over-free it, yeah. You can't free twice just to be safe or something. Exactly. So theoretically, this is straightforward. Every time you allocate, just do a matching free. But it's not that straightforward because you don't know when you're done with that block. Right? We're not allocating just for some temporary storage for the next 5 lines of code. We're allocating because it's part of our data structure, our list. And we don't want to release it until the user deletes the node or we're done with the whole program. So we got to have a way to get to everything. With a list, it's straightforward because all the nodes we've allocated can be accessed from the Sentinel. You follow the links, you get to each node. But with other data structures, it may not be as straightforward. And it's really, really easy to have memory leaks. It's really easy to be done with something but not realize you're done with it. Basically lose the pointer to a block of memory and not realize that was the only thing pointing to it, and it's a memory leak. So the stuff we do in here, it'll be fairly straightforward because our structures are going to be well understood by us by the time we're coding them. But sometimes it can be really, really sort of subtle and sneaky. All right, so we can talk more about that later. So let's look a little bit at code. Let's look at a traverse function for printing the contents of a linked list. So in PA1, it probably looked something like this. So I suggested, it's not required, I suggested having a variable header that's equal to 0. That's the address of the Sentinel. So we set temp equal to header. Well, let me write actual C code. Temp equals LL bracket header dot next. And then while temp is not my null, we want to print the data field. So LL bracket temp dot data. And then we want to move to the next node. So we say temp equals LL bracket temp dot next. Okay, what would this look like in PA2? Assuming that header is pointing to your Sentinel node, this is temp equals header arrow next. And then while temp is not equal to, and we're not using my null anymore, we're using the actual system null. So while temp is not null, well, we want to print the data field of the node temp, so that's just temp arrow data. And then we want to set temp to the next node, and the next node is temp arrow next. So temp equals temp arrow next. And there's a nice parallel structure between these, right? It's a line for line translation. Basically, instead of saying ll bracket temp dot next, we're saying temp arrow next. And instead of saying ll bracket temp dot data, we're saying temp arrow data. And instead of saying ll bracket header dot next, we're saying header arrow next. And really is that straightforward. But I don't want you to just blindly go through and change all of these into all of those. My suggestion for PA2 is actually write each statement thinking about what you want it to do. If you've got comments on your code, this is going to be perfect, because you're going to see something that says have temp point to the node after temp, and in your mind that should say, okay, set temp equal to temp arrow next. So you can make a copy of your PA1 code and then go into the editor and start rewriting each line. But it might be interesting for you if what you do is make a copy of the line, comment out the first version, and write the second version, and start seeing this kind of translation. And eventually that's going to click. And you're going to sort of internalize the idea that this is really just using temp as an index into the memory array and picking off the next field. This is just like memory bracket temp dot next, if you like. You can go through and blindly substitute all of these with all of those, and you can actually do it with a regular expression and get it in one fell swoop. But it's not, well, that is kind of fun, but it's not as instructive as actually writing it like this. All right, so play around with that. Let's write some code. Yes?
Don't know if I missed it, but why don't you have to include the LL on the right side as well?
There is no LL.
So it's just, oh, that's right.
Right? LL was an array of struct nodes.
Okay.
This time the memory is actually our array of struct nodes. Okay. So let's make a sample program here that's just going to read numbers from the user and put them into the beginning of a linked list, and then print out the list. So we're not going to do the actual add function. We're just going to keep inserting in the beginning. And we're still going to have a sentinel node, but if we insert the numbers 5 and 10 and 2, this is what our list is going to look like. We put in a 5, and then we insert a 10, it goes right before the 5. We insert a 2, it goes right before the 2. So we're just going to keep inserting in the beginning of the list. And when you start drawing pictures of lists, right, you can get away maybe from doing this and really just think of your list as like this. And when we get to trees, we'll never be drawing pictures of the next field and so on and so forth. We'll just draw numbers, whatever's in the data field, and arrows to show what they're pointing to. So let's spin some code. So list is going to be my Sentinel node, and I'm going to call malloc, get a chunk of memory. So that's the Sentinel. I'll put a 42 in the data field just so we can identify it. And I'll set the next field to be null. So we'll have an input field. We'll have an integer. We'll prompt the user for a number. And we'll do our usual CSE 124 way of reading input in a loop. So we'll call fgets, get a string of characters into input, and if it doesn't return null, we'll keep looping. So this is our standard input loop. If you hit Control D, it'll take us out of the while loop. So we'll get an input line, we'll convert that as an integer into our number, and we'll assume there's no typos. Don't ever do that. Check the return from scanf, make sure it's 1. We don't have that much time. So we've got our number. So let's add this to the start of the list. And instead of making a function and prototyping it, I'm just going to do it right here. We'll just go ahead and do our insert. So here's our list so far. So list is something. It's got a 42. That points to some data node. That points to some data node, and so on. And we want to create a new node and insert it right here, right after the Sentinel. So we got to do what? Create a new node. Okay, that's our block there. We've got to set the data field. So make this whatever number we're inserting. And then how do we put this into the beginning of the list? We got to do 2 more things.
What's the question again?
How do we insert this block into our linked list?
Change it arrow.
Change which arrow?
You have to
Okay, change the first arrow to point.
arrow that point
To
to the
data.
address of the block.
Okay, so list points to the new node. That does this. And what's the other thing we got to do?
Change the nest to the data again.
Yeah, so we need this to point to whatever was the first node. So the new node points to the previous first node. So let's do those in order. So struct node new equals malloc size of struct node. And assume there's no memory error there. New data equals, what are we storing? We're storing number. So set the data field in the new node. If we say list arrow next equals new, right, that's setting up this arrow right here, so the Sentinel points to our new node. And then the slightly tricky part is we need list to point to, we need new to point to what was the first node. So how do we figure out what the first node was? So we want to find the address of this block. And we don't have a way to do that right now. There was one way to find the address of this block. That was to see what list was pointing to, because list was pointing to this. But once we change list to point down here, there's nothing that's pointing to this block anymore. There's no way to find its address.
Which means we need to save it before.
So we need to save it before. So we could save list next into a temporary, and then we could set new next equal to that temporary. Or we could just set new next first and then change the sentinels next. So let's do that. So new next equals list next. So we'll set the new node to point to what was the first data node. And you got to do this before changing the sentinel's next field. Okay, then we can change list next to point to our new node. And then we can just say enter another number, and that's our whole while loop. So let's run this in GDB. And let's put a break at line 30. So it'll stop each time that it finishes inserting. So we'll say run. So enter a number. So we'll put in a 50. We'll continue, put in a 40. We'll continue, put in a 30. We'll continue, put in a 10. We'll continue, and we'll put in a 10. All right. So we've built a list that should be Sentinel 10, 20, 30, 40, 50. If I look at list, it's equal to 60, 20, 10. If I look at what it points to a struct node with a data value of 42 and a next value of 60, 28, D0. If I examine this memory location, it's got a 2A, that's 42 in hex. It's got a 0. It's got a 62.8D0, and it's got a 0. So the way the struct node is laid out in memory is there's an integer, there's a 0, there's the address of the next, and there's another 0. And if I print the size of a struct node, it tells me it's 16 bytes. Okay, so let's examine 4 bytes. Right, there's our sentinel. Data value, next value. Let's examine 6028D0. Right, that's this address right here. So what is the sentinel pointing to? It's pointing to a node containing a 10 and a pointer to 6028B0. If I look at 6028B0, that's got a 14 hex, that's 20, and it points to 602890. And if I look at 60, 28, 90, that's a 30, points to 2870. 2870 is a 40 and points to 2850. 2850 has a number 50 and it points to 0, that's null. So there's your list in memory. And it's stored backwards in some sense, right? The first node was down here at 6028D0. The last node was stored at 602850. That's a lower memory address. That makes no difference to us though. Our code that traverses a list, prints a list, searches through a list, never really cares what the order of these things are in memory. Okay, just like it didn't matter to you if in your PA1 your first node was stored down here and your second node up here and your third node in between, makes no difference. Because we're not going through this stuff in some sequential order, we're just following from one node to the next to the next. And if you follow from the sentinel to the next node to the next, you get through your nodes in the correct order. So we'll be spending more and more time in GDB as these structures become more complex. And in PA1 we had the option of, say, making a debug function that just printed the entire array. Can't do that in PA2 unless you print all of memory. So you're going to have to get good at going into GDB, putting in some commands to ask for locations in memory and seeing what's there. Okay, so you can start practicing that with PA2 also. All right, so have a good 3-day weekend, and I'll either see you in 2:15 in a half hour, or I'll see you on Tuesday.